and his deployment and the deployment of a critical 20 Gbps EPP optical fiber link in Kakinada, AP for LTE rollout. His adeptness in network management was recognized during the prestigious International Fleet Review at Visakhapatnam at EARFCL LT Frequency Planning in UP West Sector. Professor Kaustubh Ranjan Singh academic endeavor complements his industry experience. He is deeply engaged in research focusing on next generation wireless networks, RF energy harvesting, cooperative communication, and emergency communications for disaster management. His contribution has earned recognition, including an award in the National Geographical Program Geo Innovations Challenge for Defense, Security and Intelligence by DST. He has made significant contribution to reputable academic journals and conferences and actively participates in reviewing such publications. Additionally, he holds a restricted grade ham radio license issued by DOT, Government of India, further showcasing his dedication to advancing communication technology. With this brief, and I invite Dr. Kaustubh Ranjan Singh to take this session on software design radio. We are eager to hear you, sir. Over to you.
Thank you. Thank you.
Yes,
I believe I'm audible.
Yes, you are audible.
Sure, I'll take it from here, and I welcome the audience. And over the course of this, the previous sessions of the FDP that has been conducted by DOT, we've had great privilege and knowledge sharing sessions, which have been taken by eminent speakers. So this introductory talk on a software-defined radio is basically meant to give an introduction that how software-defined radio is basically representing a paradigm shift with respect to radio communication, wherein we are in the process of replacing or moving towards the software-based radio solutions from the traditional hardware radio systems. So the talk, so I'll basically introduce my institution. So that is Delhi Technological University. So it was established as Delhi Polytechnic in the year 1947 and was renamed as Delhi College of Engineering in 1965. And in 2009, it was reconstituted as Delhi Technological University by the government of Delhi. And as of previous year, we've secured 29th position for engineering category in the NRF rankings. And we are proud to host a variety of physical and digital infrastructure that caters to the technological requirements of the day. And we have been fortunate enough to be selected by DOT, Government of India, for setting up a 5G use case lab in the 100 5G Labs initiative. So the content on this topic is structured as follows. We'll first discuss the introductory features about SDR, and then we'll touch about the hardware requirements, followed by the software tutorial that we will implement in the SDR through GNU Radio. And then we'll finally culminate with the certain use case scenarios with respect to the 5G ecosystem. So one of the important aspects of 5G and beyond 5G networks is to provide the ubiquitous coverage even to the remote areas with technical solutions and economic in nature to bridge the rural-urban divide. So this aspect is envisioned as transforming from the digital OSs, which basically in previous times catered to the select locations, and now we have to transition from the digital OSs to a digital ocean where all persons can perhaps take the services with respect to the core services, governance, and even in far-flung and remote areas of the country. So let us see the roadmap to 5G and beyond 5G networks for the next 10 years. So we're fairly advanced in our understanding and of the various aspects of the 5G ecosystem through 3GPP release 16 and 17 versions at WRC conference in 2023, where the emphasis was put on designing proof of concept systems pertaining to the new radio, macro cell, etc. So SDR is basically envisioned as a solution under various scenarios. For example, in the case of this vertical specific radio variants, then virtualized EPC or the evolved packet core, MEC, mobile edge computing, and software-defined networks. So, with respect to the Industry 4.0, the wireless reconfigurable factory, NOMA 5G enhanced mobile broadband, and the DSP solutions for terahertz communication also have something for the SDR as well. Now, basically, we are in requirement of the software-based solutions. So let us come to the motivation part of it. So with the advent of 5G and beyond 5G networks, we have a lot of technological niche areas which offer the plethora of services having universal nature and application. They require specific infrastructure requirements, which is complicated by issues like interference, where basically the density of the connected devices is expected to reach 1 million per kilometer square. So in this case, basically a lot of infrastructure does not need to be physically based. Rather, we can have some software defined elements, so which can help us to avoid cost also. So for example, let us see even on a smartphone, we have a lot of signals that the smartphone basically has access to, be it GSM, LTE, Wi-Fi, Bluetooth, and GPS as well. So all of these require different infrastructure with respect to hardware requirements, etc. Similarly, inside the home, we have the services requiring the Wi-Fi connection, Bluetooth speakers, alarm system, garage door, baby monitors, etc. So these basically, if we can have a software reconfigurability in these, basically we will have the better utilization of the hardware, and we need not replace all elements at once. So therefore, the software reconfigurability is basically the need of the hour. So SDR, basically, the most three reasons to use the software-defined radio technology is as follows. First, basically, is it offers unlimited flexibility in terms of supporting various standards. So it eliminates the restrictions of standard-specific, customized hardware radio solutions. Second is, it is a one-stop solution for multiple applications because it offers easy adaptation for a wide range of ecosystems that offer wireless connectivity and capabilities with giving good performance levels. So it guarantees the unique combination of the maximized flexibility and system integration. Third is basically the cost efficiency. Now we need not replace with the hardware very often. Why? Because we have introduced the reconfigurability parameter in a hardware. So that means we are saving on infrastructure cost to a very big extent. So what are the applications? So the applications include the niche telecom technologies of the day, especially with respect to 5G and 6G networks such as NOMA, terahertz communication, and rateless codes, etc. Then second is the defense communication. So defense communication, the reconfigurability with respect to communication architecture is of paramount importance. Why? Because, for example, if one particular communication channel is blocked through jamming or some adversary action, we should be in a position to reconfigure our transmission channel at the earliest without having difficulties. Then obviously in the public safety and disaster management, it takes the reconfigurability of SDR proves as an asset in providing the satellite network communication in the cases where the ground telecom network is affected. So therefore, the SDR, now we can say it combines the versatile hardware components with software environments in order to achieve efficient prototyping and development. So let us see how we can define SDR. So it is first a collection of hardware and software technologies that enable the reconfigurable system and architectures, which can be dynamically programmed to reconfigure the characteristics and requirement of the equipment. So it also provides an efficient solution to the problem of building multi-mode, multi-band systems. And obviously, we can use the same piece of hardware, which can be modified to perform different functions at different times. So let us see what are the distinguishing features of SDR. First is the programmability. So as protocols evolve, a platform is reprogrammed by simply adding or exchanging parts of the design. So for example, when 3GPP issues an update for LTP for a LT standard, so instead of replacing the entire SDR, so instead of replacing the entire radio architecture, SDR can be reprogrammed to accommodate those changes. Second is flexibility. So it implies that the SDR is well capable of supporting the tighter timing and frequency requirements as we evolve from 3G to 4G, 4G to 5G, and beyond 5G networks. So modularity. So modularity, SDR platform is readily deployable. So for example, the change in decoding architecture should be done comfortably without having to worry about the overall design. Then coming to the cost and the computing power, it should be uh, cost effective, having programmable hardware, and it should be able to efficiently program the protocols. So what does SDR look like? So this basically consists of a block diagram. So here basically we can see there is a hardware front end that is called as a daughter board. So it consists of transmit and receive antennas. So in this case, we have two receive antennas and two transmit antennas with respect to daughter board of this SDR, followed by a ADC and a DAC pair for each of the daughter boards. And then they are in turn connected by the FPGA board, which is then connected to the host computer through a USB controller. So what happens is basically SDR acts as an enabler to provide flexible radio front end with ADC and DAC. Then we can stream digital samples to and fro from the machine. We can control hardware parameters from the software. At the go of a click, basically we can change the parameters such as the operating frequency, the bandwidth, the amplifier gain, the sampling rate, and we can design digital processing softwares. Basically, we can implement different types of filters, modulation, and perform synchronization operations. So let us see the history of this SDR. So the SDR was coined by Joe Mottola. So until the 1950s, basically, when basically we were doing processing in the analog domain. So the modulation and filtering were performed specifically with the hardwares. So designing, in this case, a robust communication system was very time consuming and costly, and the economies of scale did not allow it to flourish further. But with the rapid evolution of this digital technology, especially with the advent of ADC and DAC converters, it became very easy to perform these baseband operations very easily on the digital domain. And then therefore, the SDR as an industry basically has taken a serious insights into industry. And then we have gone for mass production of transceivers having greater flexibility and system functionality. So this basically represents an evolution on the radio. On the left-hand side, I have the processing technology with respect to the processors, DSP, FPGAs, and GPUs. And on the right-hand side, there is the SDR technology that has evolved with time, all the way from 1970 to 2020 and beyond. So you can see on the left-hand side, as and when the signal processing has got better and better, we are able to more softwareize the radio aspect of it. So let us see what a SDR traditionally looks like. So this is the overflow of the wireless communication channel. So herein we have a digital source, which provides the input, and then we perform the source encoding. So in source encoding, what we do is basically we try to remove the redundancy in the source information. So that is basically the compression. Further, by adding certain error bits, by adding certain parity bits, we perform the channel encoding, and then we go for digital modulation. And then this digital signal is then converted to analog through the DAC, and then it is transmitted through the RF front end transmitting antenna through the channel, which basically is a noisy channel, that is the additive wide Gaussian channel, Gaussian noise channel, and the reverse is done at the receiving end. So a software-defined radio is divided into two main parts. First is the analog front-end part. This part, which basically performs the frequency of related operations, which is followed by ADC and DAC with respect to the transmitter and receiver. Second is the digital domain, basically, which basically is responsible for maintaining the signal process flow graph. So the operations such as the demodulation and modulation, filtering, encoding, decoding for the channel and the source is performed all in the digital domain thanks to the advent of the signal processing techniques. So just for the information, let us see how a conventional radio looks like. So basically we have an antenna followed by the filters and the low noise amplifier, which is denoted by this red, followed by a mixer to down convert basically. So this is shown by the green area, followed by, so after the process of down conversion, we convert the incoming frequency into the intermediate frequency, followed by the amplification, and then we perform the demodulation, and we have the output in the form of a speaker. So let us now compare what the SDR and conventional radio looks like, what are the pros and cons. So with respect to SDR, the pros are it is very flexible in design. That means we can have multi-band, multi-mode operation. Then it is reconfigurable and upgradable during mission lifetime. So what is the disadvantage of it? So it has some complexity with respect to the software implementation part. And then it is vulnerable to software threats, for example, privacy and all. And then basically it is little bit expensive. Why? Because we are in requirement of DSPs and FPGAs with and ADCs having higher bandwidth requirements. And then its power consumption is high when we compare it with respect to the traditional radio. Whereas on the traditional radio, we can see it has a limited processing and capabilities, and the selection of the processor, controller, and ADC is less performance critical, and therefore it is cheap and readily available and consumes less power. And what are the disadvantages or cons of it? So it has a very fixed design. So it has a single band or a single mode operation. Then it has, instead of having a software complexity, it has a hardware complexity. Now, hardware complexity is basically a little bit more disadvantageous than compared to the software complexity because of the reconfigurability parameter. And therefore, it has more hardware and analog components, and the crosstalk therefore occurs between the narrow bands. So the schematic I've discussed, basically it is the bird's eye view of the SDR and its hardware design components. So we have discussed previously, it consists of two transmitting and the receiving daughter boards, which is connected with ADC and DAC, and then in turn connected to FPGA, followed by the computer connection through USB controller. So this basically, this is how, with respect to the hardware front, the SDR looks like. So in the center, we can see there is a Altera FPGA, followed by the daughter boards. There are 4 daughter boards. This is the first receive daughter board. This is the second receive daughter board. This is the first transmit daughter board. And this is the second transmit daughter board, followed by the ADCs. Here, the specification of this SDR is as follows. It has 4 ADCs with respect to 12 bits, and they can sample at 64 megasamples per second. And DAC, we have 14-bit with the sampling power of 128 megasamples per second. And we have Altera FPGA, 2 receive daughter boards, and we have 2 USB 2.0 interface to host the PC. Further, now through GNO Radio, that is one software that we write the code for implementing the software-defined radio. The user-defined code basically is transmitted to the something called as a USRP, Universal Software Radio Peripheral, through the USB. So, and on the transmission end, we have a motherboard that supports up to 4 daughter boards. Further, this USB transmission occurs to the USB 2.0 interface, which can support 32 megabits per second across the USB, and the samples are in phase IQ complex phase format. Further, the FPGA basically it consists of digital down converters with respect to the receiver side, followed by filters, and with respect to the transmit side, we need a frequency up conversion. So therefore, we have the digital up converters, and followed by the DACs. So DACs I've previously discussed. We have the 14-bit DA converters with the clock frequency of 128 megasamples per second. Now, with respect to ADC, we have 4 12-bit AD converters whose sampling rate is 64 megasamples per second. Now we will discuss some common RF front-end architectures which are used in the software-defined radio. So what is the primary criteria for selecting any RF front-end architecture? That is complexity, power, and the number of components used. So let us see first them one by one. So first is the super heterodyne architecture. So in this, the RF signal is translated to the lower intermediate frequencies in multiple stages by mixing it with the local oscillator signal. So there are two stages and two local oscillators involved. So the RF signal is passed through a band pass filter and amplified by a no noise amplifier. So before passing this, basically, we are to ensure that we have an image reject filter in the form of a band pass filter, which is located at FLO plus FI1. So if this step is omitted, what happens is it will fall directly on the IF after mixing and thereby corrupt the channel information. So what is the disadvantage of this? As you can see, there are a lot many analog components which are required. Further, the choice of this intermediate frequency also depends upon certain trade-offs among the parameters such as amount of noise, spacing that is desired between the band and the image frequency, and the loss of the image frequency register. The second architecture is the zero IF architecture. So in this case, basically what we have is, it is also called as the homodyne architecture. In this, the RF signal is directly translated to the baseband by mixing it with local oscillator signal whose frequency is same as the carrier frequency. So we directly obtain the frequency that was transmitted directly through zero IF. So what is the advantage? Here, basically, no image reject filter. You can see it is required compared to the previous one. Here, the image reject filter was required. Here, no image reject filter is required. Also, the components that is ADC and low noise amplifier, they operate at significantly lower frequencies. Okay, so therefore, their integration with respect to hardware is easily possible. Then the isolation between the local oscillator and the input of the low noise amplifier and the mixer is not infinite. There is a finite amount of feed through that occurs from the local oscillator, and that is referred to as the LO leakage. So this leakage basically is shown in the form of something called as the DC offset, and this causes the corruption of the transmitted baseband signal. What is the solution for this? Then we have something called as the low IF architecture, which is a blend of the both receivers, that is the heterodyne architecture and the zero IF architecture. So in this, basically, it is a hybrid. Here, the RF signal is converted into the low IF signal, and then it is digitized. And it is down converted from the low IF to the baseband, which takes place in the digital domain. So here, basically, you can see the problem in this, basically, the self-mixing was occurring. Here, basically, it is eliminated. And because mixing and filtering is done in the digital domain. But here, what is the catch? The ADC have very strict requirements. So ADC should have sufficient input analog bandwidth, and the dynamic range must be wide enough to accommodate the signal variations to the path. Further, let us see what is the ADC. ADC basically is responsible for converting the continuous time signal to discrete. And what are the performance parameters with respect to SDR? It is signal to noise ratio, resolution, and SFDR, and aperture jitter and power dissipation. So moving further, the limitation of SDR basically is very high with respect to the development of the SDR technology. Why? Because the antenna cannot be directly connected to the ADC because it does not have the sufficient bandwidth and dynamic range of the to digitize the RF signals properly. So there is therefore a strong trade-off that is observed between the ADC sampling frequency and its performance. So basically, again, there is a trade-off involved with respect to the sensitivity and the selectivity in the form of, for example, the ADC, it is required, it should have a high linearity signal, it should have a high SNR, and it should have a high SFDR. Whereas a high SNR basically translates into a better sensitivity. The SFDR basically is a parameter to define the selectivity of the radio. Now SNR is inversely, now the jinx or the trade-off basically comes over here. The SNR is inversely proportional to the aperture jitter and the sampling frequency of the ADC. So as the sampling frequency increases, the received SNR will decrease, and therefore the performance of the overall system will take a hit. So this is where we have to make a trade-off. Now coming to digital up and down conversion of the frequency. So this is done through the ADC. Basically, it converts the intermediate signals into digital samples. So this basically is fed to the digital down converter. So what is a digital down converter? It basically is a digital mixer, and it has a digital mixer and a numerically controlled local oscillator in the form of digital local oscillator followed by a low pass filter. So what this unit does is it extracts the baseband signal from the band pass signal that comes from the ADC. So after it is processed through the digital front end, it is then sent to the signal processing block. So the other aspect is the digital up conversion. So the digital up conversion, it translates the baseband signal to the intermediate frequency. So the DAC, which is connected to the DUC, that converts the digital IF samples into the analog and IF sample. So let us see what are the advances that have happened with respect to DSP related performances with respect to the incorporation of DSP techniques in the SDR. So signal processing, all the signal processing operations, for example, encoding, decoding, interleaving, deinterleaving, modulation, demodulation, and scrambling, descrambling are performed through this digital signal processor. So, and the process of decoding the received signal, it is basically the most computationally exhaustive aspect of the signal processing block. Why? Because it has to have a higher data transfer and memory operations. A lot of them are involved, for example, in decoding and performing the channel decoding and the source decoding part. And this basically a lot of FFT operations and inverse FFT operations are performed, and therefore it is very important that we select this part in a very optimum way. So first candidate is the ASIC. So ASIC is your application specific integrated circuits. So they are unparalleled with respect to their speed and power efficiency and the computational power. They are one of the most powerful DSP things. But what is the major disadvantage? They are not reconfigurable. They are designed for a specific application. They are designed for a specific architecture. So because of these limitations, they are not an ideal candidate with respect to the adoption in the software defined radio hardware aspect. Then comes the digital signal processor. So what it is? So it is a specialized microprocessor that is designed specifically for the digital signal processing that occurs in the real-time computing. Now, on a performance scale, they fall between the ASIC, which is the best, and the FPGAs. So they have moderate cost and they are the backbone of the most SDR systems. So this basically, what is the shortcoming of this? The shortcoming of this is the limited parallel architecture that is supported through this DSP. So this forms a bottleneck when it comes to the implementing the parallel operations. So this basically has opened the door for something called as the FPGA, that is the field programmable gate array. So this is nothing but a semiconductor device that contains the programmable logic interconnects and programmable logic components. So what is the functionality? The functionality of the basic functions can be done by programming the logic components and the interconnects. So it can be written in the VHDL or Verilog, and they are usually slower than the ASICs and more power hungry. Why? Because they perform the parallel operation in a very efficient manner. So let us now see what is the comparison of the SDR design approaches with respect to the hardware adoption of the signal processing domain. So first is the computation power. So DSP, for example, I've taken the Texas Instrument C66X. So and in the FPGA, I've taken the comparison with respect to the Xilinx Vertex. So with respect to the computation, we have fixed arithmetic engines And whereas on the computation part with respect to FPGA, we have the user configurable logic. Then for execution, they have limited parallel support, whereas the FPGA offers high parallel support. Then throughput is high in case of FPGA, then cost is high in a case of FPGA because of the parallel architecture that it offers. So what is the classification of the software radio? So we will see how the softwareization, the advent of softwareization with respect to the hardware conventional radio has taken place. So in different steps or different tiers. So the first tier is basically your hardware radio, that is the tier 0. So that is the first generation classic super heterodyne architecture. It includes two down conversion stages. So there was little or no scope for softwareization. Then came the software controlled radio, which formed the tier 1. So in this, basically the control functions with respect to the interconnects and power levels was possible with respect to the reconfigurable operations, but it was highly limited and it could not extend to the frequency band or modulation types. So limited functions are changeable using the software. Then came the software defined radio as we know of today. So it basically, we can have a good control over modulation techniques, wideband and narrowband operations, encoding, decoding, etc. So signal path is reconfigurable without hardware modifications. And frequency bands are still constrained at the front end. Why? Because it is attributed mainly to the performance limitations that is imposed by the ADCs. Then tier 3 basically is the ideal software radio. In this, basically the programmability extends to the entire system with analog conversion only at the antenna, speaker and microphones. So there is a digital end-to-end except for the front-end parts, that is the antenna, speaker and phones. So it is far from reality, again due to software limitations such as ADC and sampling rate. Then comes the blue sky vision, basically we can say, or the ideal software defined radio, basically that is referred to as the tier 4, where everything is basically is in the form of it is basically in the form of an ideal software defined radio, and it requires no external antenna and has no restrictions on operating frequency. That means we have on chip, we have antenna on chip to give the network on chip communications. So we can see that the shift from the traditional hardware radio has occurred, and we are in the process. We have overcome the limitations with respect to the frequency that were imposed in the SCR. Now we are at the tier 2, that is the SDR. Our aim is to go towards the ISR. So now we can see what are the hardwares that will support the operations and functionality of the SDR. So first is the NI-based Universal Software Radio Peripheral. So it was developed by Mark Itus to implement the SDR systems. It is made up of 3 sections. First is the radio frequency antennas, then the motherboard, wherein we have the FPGAs for DSP and the daughter boards for transmission part. So this is done with respect to the FPGA and memory. So let us see what they are. So the first example, basically, now you can see the range of this USRP is from 1 megahertz to 7.2 gigahertz. So this is offering a lot of flexibility in designing the front-end communication systems, wherein earlier, basically, if we had to replace, we had to change the antenna and the entire supporting hardware architecture. Herein we have the entire range of the radio communication, which we are currently operating and we are aiming to operate in the future. So this is extending up to 8 gigahertz, and it has a good channel bandwidth of 1 gigahertz, 1.6 gigahertz per channel, and 8 TX-RX paths are available. And the clock timing is basically, we have a dedicated GPS antenna offering the GPS clock into it. So here it can support the development tool softwares such as LabVIEW, Open, which is proprietary software. Then we have GNU Radio and open source UHD. And again, it can support MATLAB software, which is again a proprietary software. Again, so moving further, so this is how basically the software-defined radio looks like. So the that is with respect to NI-USRP. So this is its internal architecture. Here we have the transmit antenna, and here we have basically for timing synchronization output, we have the connections. And here we have the gigabit Ethernet port, and we have a option for GPS clock also, and we can have model signaling from 50 megahertz to 6 gigahertz. Now there is a family of products that is offered by NI. So here basically I've listed some of them, and some of them might be even listed. Some of them might have been uh, uh, issued in the market, and this list is not yet updated. So here you can see you have 8TX RX, and depending upon the requirements, you can choose the different hardware architecture. So for an example case, I've taken an interactive dial tone. I'll be coming to this GNU radio in the later half of the talk. So this can be implemented through NI-USRP, and this is how basically the frequency spectrum of the interactive dial tone looks like. Second comes from the analog devices, that is the offering of the Pluto SDR. So one example I've taken with respect to AD9363. So this has a flexible rate and offers a 12-bit ADC and DAC architecture, and it is very handy, small enough to be put in pocket, and basically you can have a GNU radio source and sync blocks, and it has up to RF range coverage from 325 megahertz to 3.8 gigahertz. Again, we have a different family of products that are offered by analog devices. So they basically, as per the requirements, we can choose the hardware. As an example, with respect to the GNU radio, we can see the AM radio spectrum through Pluto SDR. So here basically the output you can see. Basically this is the talk radio speech, and this is basically called as the waterfall diagram. So here in this spectrum you can see and the different AM radios stations from the antenna purpose. Third one is basically a dongle based offering from the RTL. So it has 8-bit ADC, and it is offering a receive only operation, and it has frequency range which is limited up to 2100 megahertz. So it is working in a receive only operation. So there are other platforms as well, for example Hack RF1, Lime SDR, and many more. So depending upon the use case requirements, we can go forward for appropriate choice of the hardware. Now we come to the software part of it. What are the different softwares which enable us to perform the functionalities of the SDR? So first one, basically, we have the C++ at the USB, a C++ based USD API, which is again open sourced. Then we have the GNU radio or the GNU radio. So here we can work using C++ and Python also. It is again open sourced. Then we have proprietary softwares in the form of the LabVIEW offered by the National Instruments, and MATLAB offered by the MathWorks. Obviously, we have some the application specific softwares with respect that support the SDR functionality. So with respect to cellular operations, we have OpenBTS, we have OpenBTS UMTS, OpenLTE, SRSLT, and Amarisoft. And then with respect to performing the satellite operations, we have GNSS SDR, GPS SDR SIM, and Skydel Solutions SDX. And then with respect to amateur radio, we have the SD SDR and SDR hash and SDR console. Let us see how we can go forward with respect to the MATLAB, how we can interface MATLAB with respect to a particular hardware. So what we are required to do is we are required to add on a hardware package. So depending upon the hardware that we have, for example, in RTL SDR Studio, there are different hardware packages available with respect to the different hardwares. USRP radio is there, then Xilinx based Zinc is there, then ADLM Pluto radio is also there, then so on and so forth. So this basically we can add on, and then we can perform the operations. So for example, using one Pluto SDR, we are trying to transmit and receive a sinusoidal wave. So it looks something like this when we run the program through the spectrum analyzer. So this basically is the sine tone. And here, when I talked about the architectures offering the leakages, LO leakages, so there basically we saw the DC offset and IQ imbalance, which is represented over here. So this has to be minimized. Okay. So moving further, we have the LabVIEW. So the LabVIEW is basically a tool from the National Instruments. So that offers a visual programming environment for test automation. So it is similar to the Simulink that is offered by the MATLAB, and then it is similar to GNU Radio. So for example, in this case, we are taking the case of FMD mod. We'll come to the implementation aspect in a while now. So for now, basically, for example, in this, we have FMD modulation. We'll select it. And then this is the, and then we'll connect the hardware. That is the USRP. And then through the control button, we can see and listen what are the operating frequencies nearby. So for example, in this case, NI2 2900 was used, and then we can use this through the sound card. So let us see a comparison of the software tools that are required for the SDR implementation. So first one is basically with respect to MATLAB and Simulink, then is GNU Radio, and then we have the LabVIEW. So input with respect to MATLAB, it is code based or graphical based. Then with respect to GNU Radio, it is graphic. It supports graphical in the form of flow graph. Then we have the Python and the C++ implementations also supportable. Then with respect to LabVIEW, we have the graphical support also. With respect to output, we can export it as C++ RTL. Then in respect to GNU Radio, C RTL, and then LabVIEW C RTL. Then what is the platform that is supportable? Then we can usually go forward with respect to, this is a common aspect. So we can go forward with respect to any DSP and FPGA. We choose to go forward to work with all the softwares, that is MATLAB, GNU Radio, and LabVIEW. Coming to the license part, the MATLAB and LabVIEW are proprietary based, and GNU Radio is open source based. We now come formally to GNU Radio. What it is an open source software which is available for software defined radio and signal processing. So it was founded in 2001 by Eric Blossom. So it is basically a block-based data flow architecture. So each block, it runs in its own thread. We have data flows that are generated through a graph that is referred to as a flow graph. And then we have the blocks that are the nodes, which basically are implemented through C++ and Python. So we can, there are three options. Let us see what they are. And before that, we'll see the tier 3 architecture of this GNU Radio. So with respect to the application development and creating flow graphs, we are in requirement of the Python language. That basically the Python flow graph gets generated when we hit the run button. Then we have the second tier, that is with respect to the signal processing modules. They are written with respect to C++, and then we are using the software wrapper, that is Twig. And then we already have a library of signaling blocks, and some of them are under development through open source efforts of the community. Then we have something called as a scheduler to control the flow graphs. So that means we have threading available, that is to control the starting, stopping, and waiting operations of the signal flow graph. Now, how can we develop things through GNU Radio? First is the Lego way. Lego way basically is putting all the components together and joining them. So that is easy and intuitive. And then we will then create the flow graph by connecting the existing components in the GNU Radio Companion. So GNU Radio Companion is a software. We'll see in a moment how this look like. Then second option is the C++ way. So if you are comfortable with working with C++, we can have more customizations possible than compared to the Lego way. And this basically offers faster execution. And then it is wrapped to Python using the SWIG, that is the simplified wrapper and interface generator that generates the flow graph. Third is obviously the Python way. It is also fully customizable, faster in development, and we can use NumPy, SciPy, and it is ready for prototyping as well. So let us see what signal flow graph looks like. So they are nothing but transceiver architectures. They are implemented as flow graphs. So they are similar to the design of the Simulink and LabVIEW. So they define the structure and parameters of the block. So this basically is an interface that we've taken. So they are different blocks such as signal source, complex to float operation, then throttle, and then QT. For visualization, we use the time sync and the frequency sync. So connecting these basically basically blocks basically generates the something called as a signal flow graph. Okay, so what is a block? So block is basically an entity that is written in C++ or Python, and then they implement a logical function. For example, add is a block, so it can be implemented. Basically when you click it, the properties, you can change. Right now it is showing a 2 input, 1 output. So you can have multiple configurations, and it is basically programmable. Okay, so there are different types of blocks. And this is how basically when you open the GNU Radio Companion, this is the window or the console that looks like. So you have a space over here that you can go forward and make your flow graphs. Over here you have the console. When you run the signal, you will see some messages regarding the successful implementation or what is the issue, and then you can go forward with debugging. And then what are the variables that are present over here that you can take forward with. Okay, so I mentioned blocks over here. So there is a host of blocks that are available in the library. So here on the right hand side, here basically on the library, so there's a search button. You press this and you can see different types of blocks are available with respect to your requirements. For example, when I type noise, so it shows me, for example, I want to take a AWG noise source. So I have a inbuilt block basically that is in the tree. Noise source. So I'll just click it and then it appears on my screen in the edit flow graph. What are the data types? This color coding is done in order to show what the different types of data types are supported by a particular block. So usually denotes the complex operations. The orange basically is denoting the float, and this pink or purple basically is denoting the byte operation. So for example, this block that is referred to as the Qt GUI frequency sync. So it is currently under a complex operation and with respect to a frequency sync. So so it is changeable also. So we can change it. And now you can see it is a float type based. It will support the float operations, and it will show the frequency spectrum also. Now we can also change the block properties. So every block has a property that can be viewed and set. So for example, in the case of when we type signal source, so we can change the sample rate. So sample rate is defined by either through a variable, or we can define it through a manually also. Then output type, either we want it in complex form or float form, etc. Then the type of waveforms that we want. So some traditional waveforms that are that we usually use, usually the sinusoidal signals, they are available. Then the frequency, the amplitude again can be set either through a variable or through values. Then some offsets that you want with respect to the phase also, and some message. So these things are customizable with respect to the block. So let us see some different types of source blocks. So first is the signal source block that we just talked. So this basically this basically looks, just discussed it. So different types of source blocks are there. So if you want to generate a simple signal source that is either a sinusoidal or cosine based, so you can just find the search in the block library for a signal source, and then you can go forward with it. Apart from that, with respect to implementing noise operations, so we have so when we design a communication system, noise is an inherent parameter that we have to take care of. Why? Because it leads to a lot of errors while transmitting. So we have the additive white Gaussian noise that we usually go forward with modeling with respect to the communication systems, and then we can go for different types of noises are also available with respect to this noise source. Then if you want to generate a stream of zeros, we have a null source block. Then we have an audio source block. Audio source block basically can take the input from the host computer's mic. So that is how it is envisioned to function. So this was with respect to the source blocks. We have the sync blocks. So the output can be written to a particular file type also. So it can be used using the file sync. Then we have the audio sync. Audio sync interfaces with the sound card, and then we can listen to the the message that was transmitted. Then we have the options block. So whenever we open this GNU radio companion, so on the left hand side we will see certain predefined things such as option block and the variable block. So let us see what it is. So basically, the properties are described as follows. It shows the title of the flow graph, and then we generate the options for visualization purpose using QtGUI, WXGUI, no GUI, and then it limits. We can have a maximum limitation. Yes, yes, yes.
There is a raise hand by Dr. Sanjay Kumar. So,
yes,
Sanjay
yes, yes.
ji, if you can ask.
Yes, yes, please.
Dr. Sanjay had raised hands. I don't know whether he's still there or.
Okay, I'll continue in the meanwhile. Okay.
Yeah, yeah. Please continue. Thank you.
Apart from that, we have multi-rate signal processing scenarios also. So sometimes it might be required. We have to match the sampling rates of two different signals. So we can do that through the decimation and the interpolation operation. So is the 1/pth of the original faster sample rate. So it is obtained decimator. So basically it is nothing but a low pass filter followed by a downsampler. So here we can see the decimation or the reduction in the sample rate operation through an integer factor. Then we go forward if we have to interpolate or we have to increase the number of samples. So what we do is the processes we implement, we add p-1 zeros between the input samples and we perform the interpolation. So then therefore the output sample is basically p times the original slower sample. Then basically in a block diagram, if you can see, the interpolator is basically an upsampler followed by a low pass filter. Then we have the frequency translating filter also. So basically this performs a frequency translation and then downsamples the filter by we can run a decimation, and then we can use a channelizing, and then we can use a bandwidth. We can appropriately use the filter to get the structure. All right. So with respect to the block organization, with respect to the GNU radio, so we have something called as the in-tree modules. So here basically with respect to analog, some blocks are there. With respect to the digital, we have some blocks. With respect to the filters, we have some pre-built blocks. With respect to USD, so on and so forth. This basically now we are limited with respect to the with respect to the increasing in technology, we are required to have newer blocks that are to be added. So they are generated basically with respect to something called as a out of tree modules. So we can code it and then we can implement them. Those are basically, so whenever we download, whenever we install GNU radio, all the in-tree modules are basically available, whereas the out of tree modules have to be obtained specifically. So coming to the tutorials part with respect to the GNU radio. So first, hello world basically. So what we do is we can have a mic audio signal. I'll speak something into it, and then we can see the spectral components with respect to time and frequency. So the source flow graph is as follows. I take an audio source and having a sample rate of 32 kilosamples per second, and then I connect it to the sinks. Two sinks are there. That is the QtGUI frequency sync and the QtGUI time sync. So the FFT size is defined to be of 1024. We can vary this also as per the requirement. So this is how it looks like. I'll run the video. I hope the voice is audible.
Hello, and welcome to the GNU Radio tutorial workshop.
Is it audible?
Yes, yes, it is audible, sir.
Okay. Check it.
Hello, and welcome.
Further, we have the another example with respect to a dial tone generator. So a dial tone generator is something like when we are calling someone, we are pressing the number of the mobile number. So for example, we are pressing 9, then another numbers 1, 2, 3. So what happens is those numbers are recognized in the form of the frequencies. So with respect to 1, for example, we have 2 frequencies that are generated. So one is the low one, that is the 697 hertz, and the other one is 1209 hertz. So as soon as we press 1 in our mobile phone, so we must have listened that there is a audio tone that gets generated. So it is unique for every number in the dial tone. And then we implement a noise source that is of Gaussian nature, and then we add this, and then we will listen how it is. And okay, and we'll see the spectral components also. So I'll execute this flow graph. So how do we execute? So we just run it. So I'll just play it. So when I press 1, I've now actually what I'll be doing is I'll be increasing the noise. So now you can see the difference in the, I believe it is audible. So now you can see the signal gets lost in the noise. So that is how we can change this is a slider window. Basically, we can change the amount of noise through its amplitude, and we can change the frequency also. So this is another implementation with respect to the GNU radio. Moving further, third example that that we'll implement and see is with respect to the amplitude modulation. So the expression for this basically is in the form of AC 1 plus m into cos omega mt into cos omega ct. So omega c is basically your carrier frequency, and omega m is your the message frequency. M is basically your modulation index. That is nothing but the ratio of the amplitudes of the message signal and the amplitude signal. So it is bounded by 1. So let us see how this is implemented. So we now see we are using this constant source. We have defined for this example, we have taken the modulation index as 0.5. So this is your m in this particular equation. So m into cos omega mt. So cos omega mt is implemented by this functionality. So that is your the message signal having frequency as 1 kilohertz. So when we multiply and then we add 1 to it as per this expression. So this basically can again be added through a constant source, that is adding 1. So we are done with this square bracket part. And then what we do is we do the multiplication with the carrier frequency. The carrier frequency is of the form of AC cos omega ct. So this basically is implemented through this signal source. So we can see in this case, I've taken the carrier frequency of 10 kilohertz, but we can take it further also. So this gets multiplied, and we will see how this looks like with respect to the time component and the frequency component. So now when I run this, I will see something of this manner. So this basically is showing two graphs. One is with respect to the amplitude and time variations. So here you can see my modulation index I had taken as 0.5. So this basically is showing the characteristic signal of the AM modulated signal that is transmitted. And on the spectral components, basically we can see the center frequency and the upper and the lower side bands with respect to FC and minus FC. So this is how basically we can implement other modulation type. Fourth example I've taken is with respect to the FM receiver. So in this FM receiver, what we do is we do a filtering followed by, so there is a block called as a wideband frequency modulation receive. So we implement it and we define the decimation parameter as 1. We take the rational resampler, and then we will now see the spectral components, and we will listen to it also. So how it is implemented is as follows. So okay, so this is 10.56 megahertz. That is the Gyanvani. So here you can see. So the received signal is speaking at 105.6, and at 92.7. So I've changed the frequency again. So at 92.7, so we have the big FM. So here again we can see that the receiver is tuned to the 92.7 megahertz. So if I can just play, you can listen to this. Okay, so I'll move forward. So these were the examples with respect to the LEGO way, that is just adding the simple blocks that were existing. So now we can also program the Python instance, for example, in this case of a dial tone. So now you can use any, you can use you can use either C++ or Python also. So basically now what we'll do is, in this case, we'll first import the necessary modules, and then we'll set up the signal flow graph, and then we'll perform the sampling frequency and the amplitude modulation amplitude on the sound card. So sampling frequency, in this case, we are setting it to 48,000 samples per second. And then what we will do is we will instantiate a flow graph, that is through the function gr.flow underscore graph. So this basically, so this comes from a class that is the flow graph class. And then after that, we will set up two sinusoidal tones, that is at 350 Hertz and 440 Hertz. So you can change the frequency later on also. Okay. And then we will define the destination to be the sound card in case we want to listen to it. And then we will connect the source and the destinations, left and right channel also. And then we will return. So we had created the instance of the flow graph, and then we'll be return the created flow graph. And then we will create the code to execute this flow graph through this module. Okay. So this so far so good. Now we come to another interesting aspect, that is designing the out of tree blocks using Python in GNU radio. So what happens is, with the advent of 4G and 5G technology, lot more development is done with respect to the newer technologies. Now they are to be implemented through GNU radio or other radio technology. So certain blocks have to be written that needs to implement. So a simple block example I'll share that requires development with respect to the out of tree modules. So that out of tree module. So basically, so what is the advantage? That basically it is easily maintained by individual developers. So it is available as open source in the open source form, and then we can easily install the multiple OOT modules, and they offer the faster compilation. So till now we have seen block with respect to the different parameters. So with respect to a coding aspect of it, how does the block look like? So a block needs three parts. That is, first is the setup part, that is defined through the constructor or init. And then this is called as the work function part. So this in this basically we will define what is the task that has to be written in the Python to perform with respect to the block. Then third one is the scheduler, to find out how much data in and out comes out. So with respect to the constructor or init basic and initializer, so what does it do? It builds the block and it inherits one of the block types. So what is different types of block types I've discussed, for example, source, sink, interpolator, decimator, filter, so on and so forth. Okay. So then basically we can define it with respect to the initializer. We will see it. We'll see an example. So for example, we have to design, let us say in this example, I have to design a multiplier. So what I'll do is I'll go to the search library, I'll type the Python block, and I will create a block that is with the name of the embedded Python block. So now what I do is I double click it, and then this property tab opens. Here, what I will do is I will click open editor, and then I will write some Python codes into it. Okay. So I've created a multiply block basically. So it looks something like this basically. Okay. So here basically name is multiply Python block, and we have taken the parameters. So this basically is how basically we will be designing the Python block with respect to this. So in the flow graph now basically it is renamed. So this basically embedded Python block is now renamed as multiply Python block. So for example, in this case, we are taking the multiplication factor as 4. In this case, we will see how this works out. So we generate a signal flow graph and see how this block that we have created using the Python language works out. So here on the first, basically we can see the amplitude. So here basically we have two time sinks. One will be showing the status of the original signal, and then the second time sync will be showing the amplified or the multiplied version of the signal. So here you can see the original signal is of the amplitude ranging from the +1 to -1. So whereas after passing through the Python block that we have designed, so the signal is now multiplied by a factor of 4 in the amplitude domain. So that is the amplitudes are now ranging from +4 to -4. So this is how basically we can design different blocks with respect to the different requirements of the services. Second example is again the arithmetic block. So different operations, add, subtract, we can do. So in the interest of time, I'll just come to directly the implementation. So input value basically we've taken as 5.4. Now we're adding the constant as 3.4 to 5.4. So 5.4 plus 3.4 is 8.8. And similarly, we can perform the other mathematical operations, also subtraction, division, and multiplication. So this is how basically we can design arithmetic operations through OOT blocks using Python. Third example is with respect to the rectifier design with respect to the Python block. So here you can see we can design either a full wave rectifier or a half wave rectifier, and we can use a Boolean logic that we want to implement a full wave, or is it true? Then that means it will show a Boolean wave. And then if it is false, then it will show the half wave rectifier. Now coming to another important, interesting area, that is the research areas where in 5G network, where the SDR technology can help us. So first basically is the UAV platforms. So UAVs, we know the characteristics basically of the UAVs are as follows. So they can be either remotely guided or autonomous in nature. They have the ability to sense and perceive the environment. Then we have the high mobility and ease of deployment, and different sensors we can deploy on those drones or the UAV scenarios. So now the question comes is, so how can we use this UAV as a platform with embedded with SDR and SDR ecosystem? Then how can we use it for 5G? So can we build and deploy a simple to use cheap functional UAV using open source 4G, 5G protocols to provide connectivity? So the answer is yes. So it is in the form of different use cases we can do it. That is, first, UAV. In this case, it can act as a relay node. Now you can see the transmitter. The receiver is basically falling in the shadow zone of the transmitter. So now an intermediate relay is required. So this relay, which is basically a UAV-based SDR platform, so that can act as an aerial base station, and then it can relay the transmitted signal to the intended user. So this is the first use case. The second use case is UAV for ubiquitous coverage. So here you can see now in a dense urban scenario, a lot of interfering objects are there. So that is why we cannot have a good network coverage. Sometimes it becomes difficult in having a good coverage area, good coverage, network coverage, even despite our best efforts. So in this case, UAV basically can act as a aerial base station, and that can provide a ubiquitous coverage by acting as an aerial base station. Third is the UAV for data collection. So for data collection purposes, for example, this particular UAV can be reprogrammed using the SDR platform. Okay, so what are the libraries that are available with respect to LTE evolution? So there are some open source libraries which I would want to share the knowledge with. So first one is SRS LTE. So this basically is a free and open source 4G LTE library that can be used to build end-to-end mobile networks using the software-defined radios. So this library, it offers three main components. First is the UE component, that is the SRS UE. It implements the user equipment. Second is the eNode B component, that is, it implements the LTE base station or the eNode B. Third is the SRS EPC or the evolved packet core. So that basically provides network functionality with mobility, HSS, and the gateways, that is S gateway and P gateway. And it supports the LTE bandwidths of up to 20 megahertz. And the best thing about it is all the uplink and the downlink channels basically are supported by it. So different types of downlink and uplink channels are there with respect to 4G and LTE advanced library. So okay, then coming to this module library of this SRS LTE. So it consists of something called as the core. So core modules basically are the different building blocks with respect to the physical layer. Then coming to the physical channels. So the physical channel, there is one module for each uplink and downlink channel. Then we come the above it is basically the user equipment process. So that is basically implements the physical channel for uplink and downlink. Then we have the example applications. So on the top of the hierarchy, basically different examples are there to show how it works. Then the second library, that is open source, available for implementing SDR framework with respect to LTE and LTE Advanced, is called as the Open Air interface. So it is a free and open source library that implements the 4G LTE network with the commercial off-the-shelf SDRs. So this basically it supports set of 5G new radio physical channels, for example, PSS, SSS, and PBCH and PDSCH. And basically it is focused on FR1, frequency 1 range. So the supported subcarrier spacing is 30 kilohertz and supports bandwidth up to 100 megahertz. The second use case, so this basically is with respect to the UAV, how UAV can be used in the 5G ecosystem with respect to SDR hardware using the open source libraries, that is SRSLT and this open air interface. Then second aspect, or the second use case scenario with respect to the research and industrial aspect, is the network function virtualization, that is with respect to SDR and SDN for 4G, 5G, and beyond 5G networks. So NFV, or network function virtualization, it will enable the delivery of network functions without installing much hardware equipment for every new service. So this basically has potential aspects in reducing the CapEx, or the capital expenditure, and the OpEx, or that is called as the operational expenditure. So now it enables migration from one hardware platform to the another for the standard network appliance, and it enables the virtualization of the RAN architecture and the core network functionalities, and it also supports the establishment of new mechanisms to deploy and operate the network within infrastructure. So one more good thing about NFV is basically the slicing part. So what is slicing? It allows the real-time repurposing and redistribution of network functions through the network slices. So here we can see different use case scenarios are there with respect to 5G, for example, eMBB, and ultra reliable low latency communication with respect to the this vehicular communication. So there we have again resliced it with respect to the strict latency constraints. Then massive machine type communication, that can be as an example of a smart factory. Okay, so there basically a lot of sensors are there. So there basically again the 5G network can be reprogrammed in the form of a IoT slice. Okay, so it basically then it becomes easier to implement these functions through the software. We come to another aspect of it, that is called as the software defined networking. So SDN basically it addresses the separation of the control plane from the user plane. So this basically allows us to the vendors to the carriers basically to gain vendor independent control. So what it does is, in this basically we have architecture which supports the southbound APIs and the northbound APIs. We'll see it in a moment. So different types of layers and business applications can be developed with respect to the different APIs, that is southbound and northbound. So this basically, so what are the existing standards with respect to the network function virtualization and SDR, SDN enabled networks? So first is basically with respect to SDR, it is Wireless Innovation Forum. Then with respect to Open Networking Forum is basically for the architecture development of the software defined networking. So this basically maintains the open flow standard. Then with respect to network function virtualization, we have the industry specification group, that is ISG. It is given by HC or European Telecom Standards. So this basically, I was talking about the hybrid architecture. Now we can see the open APIs are there with respect to the northbound and the southbound. So here basically we have a control layer. So that basically we have a network controller. So SDN layering architecture, we can define different types of instances for different applications. And with respect to virtualization, we have a virtual network function, VNF, that basically can be implemented through different open standard APIs are available. And then third is basically providing the device and the function support. That is the primary task where the software defined radio comes into play. Then it has some implications and challenges with respect to integrating these three distinct architectures. So first is basically coming to a common interface, then defining the standards to bridge the SDR device and the hardware that underlies for the network function virtualization. Then with respect to SDR, we have the MIMO. With the advent of MIMO, basically the challenge comes in the computation power of it and the cost of it, basically because the ADC and requirements and all are increasing to a very significant level, and therefore the cost becomes a factor in this. Then second aspect is the radio resource management. So this basically increases the system complexity with power management procedures. Then SDN. So again, there is a challenge of seamless handover because we are creating different layers. And then we have some security and privacy issues. So these are open challenges wherein wherein the academicians and the industrial partners, they can come on common ground to create certain standards to implement them. Then third aspect is called as the self-organizing network. So wherein the SDR finds its place with respect to self-organizing network. So what is the self-organizing network? It automates basically the management mechanisms related to network planning, configuration, and optimization. So there are different parts. For example, maintenance part is there. So that is covered under self-healing. That is network failure, outage, or power example. And then the other is self-learning, how the network is behaving, number of subscribers. For example, in the bouncing busy hours, we have a number of subscribers very high on the main roads of the city, and whereas in the outside office hours, basically in the residential areas, the number of subscribers are high. So this enables the reconfiguration or self-configuration capability with respect to the self-organizing networks. Then we have the monitoring. What is the signal quality? What is the signal traffic? How many handovers are successful? How many handovers are in failure? We have a set of different set of KPIs to take care of this monitoring aspect. So, and then we have the performance optimization depending upon the monitoring and the KPIs that we get with respect to handovers and receive signal power, so on and so forth. So we perform the network optimization. So this basically comes under the category of self-optimizing network, wherein SDR can play a significant role. So again, so it has different RAN architectures with respect to self-organizing networks. So first is the heterogeneous radio access networks. So here basically what we have is it consists of evolved node Bs, or they're referred to as the E node Bs, and we also have something called as the home E node B. So what it is a low power node that supports the same functionality in a E node B. Then basically it involves a gateway that is home E node B gateway, that is the signaling gateway, and they can also include the relay nodes with respect to the relaying layer. So here you can see different types of layers are there. With respect to relaying layer, we have relaying nodes. With respect to small cell layers, small cell basically is required to the it basically is under the range of 50 meters or 100 meters. So we can design a small cell with respect to a home E node B. It basically has the same operational functionalities just like the E node B, but for a limited range. And then we obviously have the macro cell layer. Then we have the software defined radio access networks, that is the SRAN architecture. So in this basically we have the signaling and the PDN gateway. So here basically you can see the S gateway and the P gateway. So in this the EPC basically is connected to the data plane through the interface, and basically it enables the deployment of the signaling gateway and the PDN gateway as forwarding engines. So we also have in this a mobility management entity, which is a carrier grade serving platform. Third RAN architecture of interest is basically a centralized radio access networks. So this basically is in the form of the modular design that integrates the the baseband units and the radio remote heads or the RRU units. So here you can see the baseband takes care of the baseband processing functions and control, whereas the RRH basically it is responsible for the radio and the signal transmission and reception from the user equipments or the users. So we have this centralized BBU pool basically, and resources can be managed and allocated on this demand. So this is the third RAN architecture of interest. The fourth one is the virtual RAN. So basically here uh, we can implement a virtualization layer. So and we can have a virtualized eNode B, and the common architecture for it is as follows. Then this SON oriented architecture is as follows. So here basically the role of the SDR basically will come in this PE node B. So let us look where it is. So the role of SDR in SON is as follows. So each programmable eNode B, here basically we saw that it is under heterogeneous RAN and virtualized RAN. The programmable eNode Bs, so this basically comes under the programmable infrastructure layer. So here basically when we see programmable eNode B from a layer by layer perspective, the internal design. So it consists of three L1, L2 and L3 processes. So L1 is basically concerned with the physical layer. That is where we can code things using the GNU radio and the SDR. Then with respect to L2, here basically we have PDCP, RLC and MAC layer implementations that again can be done through the GNU radio. Third one is the RRC and the MIH. So that again can be used with respect to the open flow architecture. Okay. Then, so these were with respect to the, now we come to the communication architectures that can support SDR based hardware features. So first one is the MIMO system. So the flow graph is as follows. Basically, only we are encoding and decoding with respect to the MIMO. So why MIMO? So the first thing is it increases reliability. So and part diversity is there. So what do I mean by part diversity is, so for example, MIMO consists of multiple input and multiple output antennas. So for example, a 2x2 configuration, it has 2 transmit antennas and 2 receive antennas. So this enables basically to have different paths. So for example, in one path, there is a high attenuation. So the second link will survive and therefore the system will not be in outage. So this basically enables us to have the path diversity. So whereas in the case of CISO operations, we were just left with at the mercy of the channel conditions because there was only a one transmitter and one receiver architecture. So we have increased throughput and many parallel channels are also available. So again, there is a trade-off involved whether to go forward with respect to MIMO or not. Why? Because so the trade-off involved is with respect to the hardware complexity that comes associated with respect to the MIMO architectures, then processing complexity, and third thing, important thing is the channel state information. So acquiring the channel state information is a very tedious task because delay in it can change the decision making process, and there is always an error component involved with respect to knowing how the channel state is. So the MIMO channel looks as follows. So we have the typical representation in the form of y equals to hx plus n. H is your channel matrix, x is your transmission symbol, so that is transmitted through the transmitter. So the transmitter has NT antennas, for example, so it is NT cross 1 matrix, and the receiver on the other side has NR cross 1 NR antennas, so the receiving matrix is NR cross 1. And the H matrix or the MIMO matrix channel gain coefficients is there, so which show the state of the corresponding link. So this is visualized as follows. So this H basically is as follows: H11, H12, H21, H31. So H11 corresponds to the transmitter 1 and the receiver 1. Similarly, H12 corresponds to the transmitter 2 and the receiver 1, so on and so forth. So MIMO techniques, how can MIMO improve the channel conditions? First is the diversity techniques. So first, we will see the receive diversity technique. The receive diversity. So what we have is basically the different types of techniques, for example, are there: so antenna selection, equal gain combining, maximal ratio combining, Then transmit diversity is there, MRT, that is maximal ratio transmission antenna selection scheme. And then we have the allow-me-to scheme, that is, so here basically we discussed that the channel state information is required. Allow-me-to scheme basically is a workaround with that, but there is a performance penalty that is paid with respect to allow-me-to scheme, that is 3 dB. So receive diversity, coming to receive diversity. So in fading scenarios, what happens is diversity order can significantly impact your performance. So we have different diversity combining schemes. First is the equal gain combining. So for example, we have two transmit antennas and two receive antennas. So basically, we will combine the SNRs from the the transmit antenna 1 and transmit antenna 2 in equal proportions, irrespective of what their SNR value is, that is determined through their channel conditions. Then it requires carrier tracking. The second is the maximal ratio combining. Suppose the link 1 is in a better channel state condition. So we will give a weight that is higher with respect to the link 1, that is higher with respect to the link 2, which is in a poor channel state condition. So there the weight will be lesser. So this basically now allows us to maximize the SNR. But the cost, but the cost involved is basically the hardware complexity. So here you can see, basically the effect of the diversity. So here basically the diversity channel, the number of transmitted and received antennas are 2, and this is basically with respect to 4, and this is the Gaussian. Okay, so coming to transmit diversity, so they give equivalent gains with respect to MRC, and they require also the CSI feedback, that is the channel state information feedback from the receiver. Then we can also create the parallel paths through pre-coding, and then using the CSI information, we can choose what are the good links over which we can transmit. So how does the MIMO and SDR come into picture with the implementation? So the solution is with respect to an example is given with respect to the National Instruments USRP. So here basically the host computer is there. So we have two transmit antennas and two transmit antennas over there connected by a MIMO cable. And then basically we have a switch, and then followed by the two receiving antennas. So these are scalable architectures. So here we can implement the diversity combining schemes to get the better performance characteristics. So recently, the world's largest SDR-based MIMO system has been implemented in Sweden by Professor Prof and Friedrich from Lund University. So what they have done is they have developed the world's largest MIMO using the National Instruments Massive MIMO application framework. So here you can see the antennas are there. So the system basically that they have uses the 50 USRP Rio hardware. Basically, it is used to realize a 100 antenna configuration for the MIMO BTS structure. So this is with respect to the MIMO. Then comes with respect to the error correcting. So SDR through hardware implementation can also help us in error correcting. So the concept of error correcting basically can be understood in this following infographic. So a person A basically tries to say the word cat to the person B. So while person is shouting the word cat, the noise is there in the channel in the form of an airplane passing by. So the receiver or the person B basically is hearing bat, which is obviously a error instant. Now what we can do is, so if the person transmits or says or shouts basically cat and meow, even if through the noise the receiver basically listens bat and meow, he can understand that yes, bat cannot meow, but it is the cat. So that is how basically the concept of the error correcting works. Basically, we have a parity bit that is appended with the message bit, and that forms a transmitted code word. And at the decoder, those parity bits are required basically in order to decode the bits. So how can we do it? So first, basically, we'll walk through a little bit of history. So first, basically, the Claude Shannon, that is the father of the information theory. So there was a paper by the name of Mathematical Theory of Communication. He theorized a framework in which the channel we can achieve maximum channel capacity with the arbitrary error rate. So by using appropriate error correction schemes. So that means he told that yes, there is a way to achieve any arbitrary error rate that you want to design your system for, as long as this equation, that is the channel coding, is satisfied. That means V log 2 1 plus Sn. So that means as long as you are in this region, that is your transmitted rate is less than the code rate, you are safe and you can design with whatever BER that you are designing. So therefore, after that, there has been a lot of effort in this direction to find out what are the optimal codes that are allowing us to achieve what is called as the channel limit, that is the ultimate limit of the communication. So in this case, I will illustrate the impact of the coding gain with respect to, here we have two graphs, two curves. One is the dashed one and the solid one. So the solid one basically is with respect to a uncoded scheme. That means we are not using any error correcting scheme. So whereas in the dashed one, we are using a particular error correcting scheme. Now we can see, so if we have designed our system to work at the bit error rate of 10 power minus 6, so we can see the EB by N naught requirements, they come down automatically from D, that is the 14 dB, they come down to the point E, that is your 9 dB. So therefore, this basically is referred to as the coding gain. So this basically refers to the reduction, the improvement in the performance of through the that is achieved through the error correcting schemes. So here also basically some different codes have been identified through the 3GPP to be the candidate error correcting codes with respect to the 5G and beyond 5G framework. So the two codes basically are LDPC, that is the low density parity check code, and the second one is the polar code. So they have demonstrated their performance to be nearing the channel limit. So let us briefly see what the LDPC codes are. So they basically are the class of the linear error correcting codes. So as per the 3GPP TSS 38.212 architecture, so two candidates have been identified. That is the polar code that has been recently introduced by Arikan in 2009. And then LDPC code, so they were introduced by Robert Gallagher. So they are recommended by 5th generation new radio. So LDPC will have a focus with respect to the LDPC. So they have the high throughput, low latency, and low decoding complexity with respect to the rate complexity. And then we will see Gallagher invented way back in 1962. So the architectural hardware limitations, they were there at that time. But as of now, recent advancements with respect to the processing schemes that are available currently, now decoders are very efficient with respect to implementing the LDPC code. So now basically they have again come back into the picture, and they are one of the promising candidates for error correction schemes. So let us see. So in this, I'll just focus on designing the encoder parity metrics with respect to a LDPC code. So there are two types of base graphs. This is the process that is defined by the 3GPP in the standards. So we have two base graphs. That is base graph 1 has 46 rows and 68 columns, and the base graph 2 has 42 rows and 52 columns for the 5G new radio. So there is something called as a ZC, that is basically the lifting size. So that is used to increase the size of the matrix. And now LDPC codes, that means basically low density. So the number of ones that are there in the matrix that are sparse, that is less. So that is basically, let us see how it is constructed. So the both base graph 1 and 2 have the same block architecture over here. So we have extension checks, code checks, information columns, and parity columns. So now let us see how this matrix is encoded. So there are certain rules to implement this. So for example, wherever in this base graph matrix, you have the value of -1. So we are required to replace it by a all zero matrix of the size ZC by ZC, where ZC is your lifting size that is given by the standards. Now each element of value 0 in this basically is to be replaced by a identity matrix. Then for all those not having the value of -1 and 0, so we have to perform the cyclical right shift. We'll see as follows. So assume that we have a base graph B having a ZC of 4. Okay, so here basically we can see. So we'll start with -1. So -1 has to be replaced by a all zero matrix. So here you can see the green ones, that is the -1. It has been replaced by 4 by 4 all zero matrix over here, over here, over here, and this over here and over here. So we have 5 -1s being replaced by all zero matrix. Similarly, 0 has to be replaced by a identity matrix. So we have identity matrix for the positions over here, 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 and here. Okay, and then we move forward with respect to 1, 2, and 3. So 1 basically represents the one cyclical right shift from the identity matrix. So now see, the identity matrix was this, that is 1 0 0 0. So whereas in this 1 basically it has been shifted right cyclically. So it has now become, the first row has now become 0 1 0 0. Similarly, the second row, which was initially 0 1 0 0, so it has now become 0 1 0 0 1 0. The third row, that was 0 0 1 0, it has now become 0 0 0 1. Fourth row, which was 0 0 0 1, that has now become cyclically right shifted to 1 0 0, and this process will continue. So using this basically, so this functionality can be easily implemented with SDR, where we can use the appropriate decoding schemes to get the good performance results. So with this, I come to the conclusion of the today's talk, that is based upon the software-defined radio, and it presents transformative opportunities for 5G networks. It enables a rapid adoption of the evolving standards and requirements, ensuring the future proofing of the 5G infrastructure. Then again, it ensures the long-term viability. So now the crux is basically taking the network to the remote areas as well. So now SDR basically is a efficient enabler in order to convert what is called as the digital OSS to a digital ocean. That means digital OSS was a selected locations where we had good networking, network capability areas. Now that basically has to be extended, and that OSS has to be transitioned into something called as a digital ocean, where all the services must reach to the all areas. So with this, I conclude. Thank you.
So thank